So if you'll remember last time, it came up with, we had a quadratic. We were solving for the coefficients A, B, and C, and we had ended up setting up this system of equations. Nine A minus 3B plus C equals negative 18. And then let's see. This is just the letter A.
Some people are trying to take notes. Yeah.
So we were looking to solve this system of equations here. Now, it's a 3 by 3 system, meaning that there's 3 variables, A, B, and C. We also have 3 equations in the system. And so inherently a 3 by 3 system is just going to be more complicated than a simple 2 by 2 system. So what we're going to see, well, how do we get this one started? Well, we're usually looking for some kind of little trick maybe. Hopefully we can get a trick. And it looks like a good trick is going to be, look at these first 2 equations here. We've got 16a, we've got positive c. It turns out if I subtract this second equation from the first one, I'm going to get rid of both the a variable and the c variable, which means I'm just going to be left with the b variable, which means I will be able to figure out one of my variables' value right away. So I'm going to take the first equation, 16a plus 4b plus c equals negative 53. Take the second equation, 16a minus 4b plus c equals negative 37. And you can either say you're subtracting the second equation from the first equation, or you can say you're adding -1 times that second equation. It's the same thing. Now I'm subtracting, and I got to subtract each individual piece. So 16a minus 16a, there's nothing there for a. A is now gone. 4b minus -4b becomes 4b plus 4b. So you're going to end up with 8b. Then over here you have c minus c, so now c is gone. That's all good stuff. And then it looks like you have negative 53 minus negative 37. So that becomes -3 plus 30, negative 53 plus 37. We know that's certainly going to stay negative because adding 37 is not going to be enough to pull it out of being negative. And it looks like that value will be -16. So through the elimination method, basically, we were able to get those first 2 equations down to something that just has the b variable in it. And now it's just as easy as dividing both sides by 8. And you end up with a b value of -2. So I'm even going to put that over here. And now that we've done that, some more wonderful things will happen. One of those things is, okay, we know what b is. Now we can start using some of the other equations in order to really start solving this. But notice, here's another little trick. if I were to deal with these two equations, equations 2 and 3, if, just kind of playing pretend, if I were to subtract this equation from this equation, I notice that the C's would go away. I know that I already know what the value of B is. I'd only be left with A, and so I could very quickly solve for A. So now what I want to do, I want to take equation 2 here, which is 16A minus 4B plus C equals negative 37. And I want to subtract equation 3 from it. Minus 9A minus 3 plus C equals negative 18. And so now I can do that piece by piece. (16a minus 9a leaves me with 7a. Then I'm doing negative 4b minus negative 3b. That becomes negative 4b plus 3b, leaving me with just negative b. And then we have c minus c, which means c goes away entirely, which is exactly what I wanted. Then I'm going to have negative 37 minus negative 18. That becomes negative 37 plus 18, which won't quite make it positive. It'll still be negative, but then you can think of it as 37 minus 18, which will be 19. So you have negative 19.
That should be minus 7b. Oh, no, you subtracted. You're wrong.
Where?
No, they read it wrong. You're fine. You're fine.
Yeah, we're subtracting the whole thing. And then, yep. So now we are down to this thing. It only has two variables, but since we already know what B is, we can plug in that value for B. So 7a minus, and now B is negative 2. Equals negative 19. And now we just got to solve for A. It's going to be very straightforward. That'll become 7a plus 2. Subtract 2 from both sides. This is just a very simple linear. Subtract it over, you'll get negative 21. And look, it just so happens you'll get some nice integer coefficients. You'll get negative 3 for A. So we've done the bulk of the heavy lifting here. We've found two of our three variables. Now to find C, the third variable, we can literally use any of these three equations. Equation 1, 2, or 3. Plug in this A value, plug in this B value, and then you'll only have C left over. So let's try out 9A minus 3B plus C equals negative 18. Let's just throw them into the third equation. It really doesn't matter at the end of the day. Now I'm going to substitute negative 3 in for A, negative 2 in for B, and we'll see what happens. So it's going to end up being 9 times negative 3 for A minus 3 times negative 2 for B plus C equals negative 18. And now you notice we just have one variable, C. We can figure out what these two become 9 times negative 3 will be negative 27. Negative 3 times negative 2 will become plus 6. Then we have plus c equals negative 18. Negative 27 plus 6 will still give you negative 21 plus c equals negative 18. Then you can add 21 to both sides to get c by itself. Negative 18 plus 21, I'll actually write it this time, so plus 21. You'll get c equals positive 3. So we just had Thanksgiving last week, a week ago today. We should be thankful that these first two equations here, through elimination method, I could get rid of 2 variables in one go. Normally I can't do that. Normally I'm not so lucky. And so the final answer, the quadratic, remember, could be written in back here. F of x equals ax squared plus bx plus c. This was the quadratic with the coefficients a, b, and c that passed through those 3 points that we started last time. So now we know what those coefficients are. Negative 3x squared minus 2x plus 3. And that's going to be the jeweled crown for us of problems from this section. All right. So that was systems of linear equations. What else might we look at? Well, determinant solutions to systems of linear equations. Determinant solutions to systems of linear equations. That sounds like some classic math doublespeak in the movies. If you ever, watch movies and they like to say a bunch of mathy sounding terms and write equations on their windows with pink markers. That kind of sounds like what that is. But let's break it down a little bit. Let's break it down together. We're going to have to talk about the idea of a matrix. A matrix. Now, some of you are probably too young to remember there was a movie in the 90s starring Keanu Reeves that was all about, it was kind of cyberpunk influenced film about questioning the nature of reality and looking through it from a different lens. And that movie was called Johnny Mnemonic from 1994, or I think 95 maybe, which has nothing to do with what we're talking about today. So anyways, we're talking about a matrix. A matrix in mathematics is essentially a table of numerical values. To put it very simply, so we use these bounds, we call these kind of giant brackets. And what we can do is we can put values in here. These are either numeric values, or if there are variables in them, the variables are meant to represent numbers. So at the end of the day, it is still numerical. So you might have a matrix like this. And what we try to do is we try to properly space everything out. We try to space everything out. Now, what you can see here, there are 2 rows. And then you can also see, and of course these lines aren't really there, it's just to help us count. There's 3 columns. Two rows, 3 columns. But the lines aren't really there. So what we would say this is a 2 by 3 matrix with these values: 3, 2, -1, 7, -14, 0. A 2 by 3 matrix. If you can't remember whether you should declare your rows or your columns first, you can say it's R by C, and you can think of RC cola. And most of you are like, no, I wouldn't think of RC cola because I had no idea what RC cola is. It was like, I don't know if it's still around or sold anymore, but it was a cola brand, you know, kind of like Coke, Dr. Pepper, and Pepsi. And it just did not pass muster. It was considered pretty good, but you know, it just never reached the popularity of Coke, Dr. Pepper, and Pepsi. So if you don't think of RC Cola, you can think of like a remote control car, RC car. But that's how you can remember whether the row comes first or the column. So this would be a 2 by 3 matrix. A 2 by 3 matrix. So we have an example of a matrix on the board. What we can do is we can take the determinant. This is going to be a new word. Of any square matrix. That is, any matrix with the same number of rows and columns. We're going to call that a square matrix. I'll even change the color on that if I can. I want to do it all, so no. So a square matrix has the same number of rows as it does columns. So let's look at an example of a square matrix. This is a square matrix. You can tell that it's a 2 by 2 matrix. So it has the same number of rows as it does columns. Both are 2. Just as a little note, sometimes a square matrix is called an n by n matrix, which just n is the same for both the row and column. So it's just another way of expressing the idea that you have the same number of rows as you do columns. So whenever you have a square matrix, you can take its determinant. Now, what the heck is a determinant? What the heck is a determinant? It's a calculation made on a square matrix only. So you can't take the determinant of a 2x3 or a 14x6 matrix. That's just, it's literally not possible. It's not defined. It's a calculation made on a square matrix that is really telling about the nature of the matrix. And that's about as far as I'll go into an explanation about it. If you ever do go on and if you study math at a higher level, you may take a class called linear algebra. And linear algebra is just entirely concerned with matrices, which is the plural form of matrix. Linear algebra, you would use the determinant. Turns out you would basically derive what the determinant actually is, and it's one way that we can prove if a matrix is said to be singular or not. But that's not a level of detail we're going to go over in this course. What we're going to do is we're going to calculate determinants because we can use something called Cramer's rule, Cramer being a famous mathematician. We can use something called Cramer's rule to actually solve systems of linear equations by putting them into a matrix and then using some determinants, which is, pretty gosh darn interesting, if you ask me, that we can use matrices like this. Now, how the heck do we actually calculate a determinant? Well, let's look. Let's say you have a matrix and because we want to make a general formula for a determinant, it depends on the number of rows and columns you have. So the determinant of a 1x1 matrix is just the only entry in the matrix. So if you have just a simple 1x1 matrix, well, that means you only have a single value in there, and so that's also going to be the determinant of that matrix. It's not horribly interesting. Now, when you're actually taking the determinant, you change the brackets to just vertical bars. So instead of using these brackets, I'm going to just do vertical bars. It's almost like you're taking the absolute value, which also is not a terrible comparison to make. So the determinant of a 1x1 matrix with just a single entry is that entry itself. It's kind of arbitrary. What else would it be? But if you're talking about a 2x2 matrix like this, A, B, C, and D, we will use to represent the entries in that 2x2 matrix. Well, whenever it's time to take the determinant, we'll change these into vertical bars. And all the vertical bars say is, hey, look, I'm taking a determinant of this matrix here. Whenever you're writing the matrix itself, you still use the regular old brackets. The determinant is going to be, it kind of works out in a weird way. It's kind of a neat little formulation. What you do is you multiply the values along the main diagonal here. So you would do A times D, or just AD. Then you would subtract off the product of the values along this diagonal. So it's AD minus BC. It's like the two eras of time are fighting against each other. So I multiply along the main diagonal, subtract off when I multiply along the off diagonal. So AD minus BC. Let's work a couple examples of that. And a determinant works, well, I want to say it works differently based on the kind of matrix you're doing. The 1x1 matrix has one rule, the 2x2. Then when we do determinants of 3x3 matrices, that's going to be a little bit harder to wrap our minds around. But at any rate, it turns out that that's actually not true, that a determinant does have a general formula that can work for any n by n matrix, any square matrix of any size. But it's a little bit ugly. It's an ugly process. So I'm not going to go into all the details behind it, like defining the cofactor and the minor and all that business, just because I think it's a little bit too intense and not completely necessary, to be honest. So I will show you how it works, but I won't necessarily show you the big wide formula. It's kind of nasty. So let's take this matrix I've put on the board here. Let's calculate its determinant. So I'm going to turn these into vertical bars. Yeah, da da. Yeah, da da da. And so now what I'm saying is I'm going to take the determinant. I got to start by multiplying these two values together. -3 times -1. And then I'm subtracting, always subtraction. And what I'm subtracting is the product of these ones on the off diagonal. Just so happens there's a 0 in there. So what this ends up becoming, -3 times -1 is +3, minus 2 times 0. Remember your order of operations. We got to do the multiplications first. 2 times 0 is 0. So we just have 3 minus 0, which is 3. So what we'd say is the determinant of the 2x2 matrix above is 3. So the determinant of a matrix is going to be just a single numerical value. It's going to be just a single numerical value. It's not going to be, a matrix itself. No, we're condensing it all into a single numerical value. And that numerical value has actual meaning for that matrix. Although, again, we'd have to spend like 3 classrooms worth of lecture in order to really kind of establish why the determinant is important. If this wasn't a college class, we'd have actually more time to do something cool like that. And again, I use the word cool, relatively speaking. So for a simple 2x2 matrix, taking the determinant as would not be so bad, Let's try out a couple more examples. Again, taking a 2x2 determinant is not bad. It's pretty straightforward. So let's do this calculation. How about I'll jump straight into the vertical bars so it's clear we're taking a determinant. -1, -3, 6, and 5. -1, -3, 6, and 5. And I can even say it equals because it's already clear from the vertical bars that I'm taking the determinant. I multiply the two things on the main diagonal. -1 times 5. I always subtract, so I always use subtraction here before I even look at what's on the other diagonal. I know it's subtraction. And I multiply the things along this diagonal now. So minus -3 times 6. And now just use order of operations, follow the rules carefully. Now, I will tell you, I will issue a fair warning here. It's very easy to make mistakes. It is very easy to make mistakes on this one, on these calculations, because there's so many minus signs basically floating around, so many negative signs, or just straight up subtraction floating around. So just be very careful, dot your I's, cross your T's. No calculation is too silly. Take it slowly. So first, -1 times 5 will be -5. Then I'm subtracting. -3 times 6 will become -18. And then I'm doing -5 minus -18, which really becomes -5 plus 18, which will be +13, because that can turn into 18 minus 5 from a different perspective. Not so bad. It's not so bad. Let's try out one more just to really drive the idea home. Vertical bar. And I'm going to get 2, -3, 4, -6. Now, before we go on with this, I'm going to make an observation. And the observation is that look at this first row, 2, -3. The second row is just the first row being multiplied by 2 completely. 2 became 4, -3 became -6. In other words, the second row is said to be a multiple of the first row. Ooh, when you have something like that in a linear algebra, in a matrix like this, you have something really funny going on. You have some interesting structure. But okay, let's do the determinant. And now I'm not going to draw the lines anymore. It's 2 times -6 minus -3 times 4. You're going to get 2 times -6, -12, minus -3 times 4 is also -12. And you're basically subtracting a number from itself. You're going to get 0. Ooh, we got a determinant of 0, which is perfectly valid. That's exactly what the determinant is. It doesn't exactly leave our hearts satisfied. But in this case, what this would mean is that if these were meant to represent the coefficients of a system of equations, perhaps like 2x minus 3y equals something, and 4x minus 6y equals something, this system would actually have no solution here. This system would have no solution, or perhaps infinitely many solutions. But either of those is kind of the nuclear option, the one you don't want to pick. You would love it if a system of linear equations just had exactly one nice, neat, clean little solution. But I'm going to tell you right now, this system won't have that. It'll either have 0 solutions or infinitely many, both of which are kind of not interesting. It just depends on what these equal, if they would create a contradiction or not. So if you have to take linear algebra, a determinant of 0 is especially really telling. So that's how 2 by 2 matrices work. That's how their determinants work. In reality, let's look at kind of a more real system. Let's look at a 3 by 3 matrix. And let's look at taking its determinant. So you have to have 2 vertical bars. And I'm just going to tell you right now, the complexity of the computation becomes much higher when you graduate from a 2x2 matrix to a 3x3 matrix. There's just no avoiding it. Our entries are going to be, let's see, 277. I gotta reference my notes here. 60291 -3. 60291 -3. Now this one's gonna be kind of funky. 3x3 determinants work a bit funkily. I don't even know if that's a word. If it is not a word, I have just invented a new word. At any rate, the way a 3x3 matrix determinant specifically is going to work is that we need to pick a single row or column to expand along. This is the exact terminology that we pick. So what we can do, we have carte blanche here, the freedom of choice, which is something that Johnny Mnemonic movie explored. We have the freedom of choice to pick any of these rows or columns to expand along. What does it mean to expand? I'll show you in just a second. You get to pick one. Now, if you don't even know what it means to expand, well, then it's probably not helpful for me to say you can choose which one. You need to know what expanding actually does, and then you can make the right choice. Let me show you what expanding does. I'm going to say, let's just stick with the first column here, and let's expand along it. What it means is I first look at, so I know I'm picking the first column, but I'm going to zoom in even more. And actually, let me use a different color. Let me zoom in even more. So I have this 2. So the determinant, and it's going to be a doozy, the determinant is going to be 2. Then I do something really funky. For a hot second, I delete the row and column that 2 was found in. And then the leftover business here, the 0, 2, 1, -3 that wasn't deleted, that itself forms like a little 2x2 matrix. And so what I do is I take the 2 and I multiply by the determinant of that little leftover matrix, the little matrix that could. Let that sink in for a minute. We are going to do this computation together several times today, so you don't have to have it all memorized right away. So we've done that. We've taken care of the first entry in the column we're expanding along. Now we've put our eyes on the 6. But there's a weird little rule that we need to do now, subtraction. We take the first entry of that column times the determinant of the leftover business. Then we subtract the next thing we're going to do. Just like it was AD minus BC, now we're going to change signs, subtract. Now we're on the 6. So I'm going to put 6 And this is going to get multiplied by what's left over after I delete the row and column that 6 was in. Again, a funky idea, but that leaves me with a matrix that's like 7, 7, 1, negative 3, and I need to take its determinant. So 7, 7, 1, negative 3. And whatever its determinant becomes, I multiply it by the minus 6, basically. Then I shift my focus to the last entry in the column, which is 9. It's going to be plus whatever that entry is, which in this case is 9. Then it's 9 times I delete the row and column the 9 was found in, and I write out the remaining thing here. That's a matrix whose determinant I'm going to be taking. 7, 7, 0, 2. That's wild. That's just wild, but that is the general formulation of what we're doing here. We still have a whole mess of computations to do now because we have 3 2x2 determinants to take. You can see then that the number of rows and columns in a matrix really directs how complex the computation is going to be. If I had a 4x4 matrix, I'd have to pick a single column or row, which has 4 entries, and then I have to take a bunch of 3x3 determinants as like a subset of that, and then each of those 3x3 determinants becomes really nasty and complex. So a determinant, we really stop with 3x3 determinants in this course. If I go to a 4x4 determinant, I could end up doing 5 to 10 times as many calculations as I would on a 3x3 determinant. If I have a 5x5 determinant, I could do 10 times more calculations than a 4x4 determinant, which was already 10 times more calculations than a 3x3 determinant. So it gets really wild really quickly. What we will eventually see, we can expand along any column or row we wanted. But if I had picked this column, it would have been a little smarter because you see that 0 in there. It would have helped me a little bit. But since we didn't know that yet, we're going to do this computation as we have it written out here. So now I say we rewrite each determinant, each 2x2 matrix. We've got 2 times in parentheses, 0 times negative 3, minus 2 times 1. We might even do something like that. And hopefully we will not run out of space. You're going to have to be something of a whiz at arithmetic here. Now we'll do it step by step, but you cannot make arithmetic mistakes. It will completely screw you over too in the long run. Minus 6 times, now we do 7 times negative 3, minus 7 times 1, plus 9 times, well, this determinant would be 7 times 2 minus 7 times 0. So let's just do it step by step. 0 times negative 3 is 0, minus 2 times 1, so 0 minus 2. Minus 6 times 7 times negative 3 is negative 21. Minus 7 times 1 is 7. Plus 9 times 7 times 2 is 14. Minus 7 times 0, well, that's just minus 0. So we simplify a little bit, minus 6 times. Now negative 21 minus 7 is just negative 28, and we can't do a lot about that. So these determinants are usually going to come out being fairly large numbers. I have to sneeze. Excuse me. Nothing like a good sneeze to wake you up in the morning. 2 times -2 will be -4. Then I have -6 times -28, so that'll actually become addition, which is good. 6 times 28, well, just do your old school multiplication. If you can't do it in your head. 168. 9 times 14, again, you can do your old school multiplication here. 9 times 14 should give you 126, I believe. Carry the 3. 9 times 1 is 9 plus 3 is 12, so plus 126. And yeah, you can do these computations without a calculator. What I will say, though, is any determinants that you have to take on the final exam, the computations will be reasonable. You're not going to get into things that are just meant to make you cry. They're going to be fairly reasonable. Now I need to do -4 plus 168, but that will clearly, well, -4 plus 168 is like 168 minus 4. That'll clearly give me 164. Then I still just got to add 126 onto it. So we can, totally do old school addition as well. 1 plus 6 plus 2 is 9. 1 plus 1 is 2. And so in a different color, I'll keep it as 290. That is my determinant here. Wowee. Look at all that. Look at all them chickens. This looks like a very difficult problem we just did. But is it really truly difficult? I would say it's more just complicated. There's a lot of moving pieces, a lot of computations that we just did. But it will get the juices flowing early in the morning. It'll get your brain stimulated and your mind working quickly. It actually really will. I was a little bit sluggish early on, but now I did this and I had to be very careful with it. And yeah, you end up with 290. Looking at this is again, look at how many little computations you did here. Look at how many you did. Do you think you're likely to make a mistake, especially as you're first learning how to do this? Yeah, you are absolutely likely to make a mistake. Everybody makes mistakes on these whenever they're first learning them. So keep that in mind. You may have the right process, but you might just make a silly little arithmetic mistake. And it's just unfortunate. The best way to get around those is to just keep doing it. Practice, practice, practice. There's no other way. And I know I'm spitting cliches like a mad scientist, but whatever. So again, I could have expanded along this column, and that 0 there would have zeroed out this middle computation. I'd get the exact same thing. I would still get 290. So no matter what, all roads lead to Rome here. With that in mind, let's try out another example of a 3x3 determinant. And this one's not going to be as bad because we're going to make a different choice of which column to expand along. So how about, let me get it written up here. How about we take the determinant of, let's use purple, a nice purple. They don't have a nice deep purple, not the band. They just have like a light baby purple, but that's okay. How about 978 9, 4, 0, 3, negative 4, 0. Okay. Now, what I can say is you can always, no matter what, if you want to just keep it simple, you can always expand along the first column. Have at you. Have at you. You can expand along the first row, and you'll get the right answer, and you won't get any points counted off if that's the way you choose to do it, because you did it a correct way. However, the smart way in this case, if you can choose any row or column, clearly I want to choose whichever one has the most zeros in it. And there's nothing wrong with that. That's not cheating. That's not, tricky. You're not being, you're not lying. You're not being dishonest. You're being smart, and you get extra points, not extra points, but you get extra imaginary points behind the back of your mind, or in the back of your mind, if you're smarter and if you work it more judiciously. So what I'm going to say is let's expand along the first row here. Now I'm going to write it out fully, but there's going to be some zeros in there that's going to make my life easier. So first I got to pick 8, and then for a half second I fake delete the row and column the 8 was in. So it's going to be 8 times the determinant of what's left over there, 9, 4, 3, negative 4. Then it's minus, always minus on the second one. And now I delete the row and column that this 0 is in. This 0 is the operating thing. So it's 0 times the determinant of the leftover business, 9, 7, 3, negative 4. Then I go to the third thing. I delete the row and column that this 0 is now on. It becomes plus, just so we know the pattern, 0 times the determinant 9, 7, 9, 4. So we have written it out completely correctly. Remember your signs, it basically goes positive, negative, positive. If this number had already been negative, you're still subtracting it, but then you're subtracting a negative. So you'd adjust for that then. But look at this wonderful business that's about to go down. This is 0 times this determinant. This determinant won't be 0, but it's being multiplied by 0. So this business right here goes away completely. Oh, happy day. That's exactly why I chose this column to expand along. And then over here, who cares what this determinant is? We're going to end up with, if this thing will show up, this just going away. So we have a much easier go of things now. It's just 8 times the determinant of that little 1 matrix, 9 times negative 4 minus 4 times 3, negative 36 minus 12, 8 times negative 48, which isn't so bad. You can do old school multiplication. You know it'll be a negative number. Once you know it's negative, just tell yourself it's 48 times 8, 64, carry the 6. 8 times 4 is 32, plus 6 will give you 38. So it's negative 384. And so the determinant of this 3 by 3 matrix was negative 384. And you just got to choose the right thing to expand along. And it's really just straightforward after that. And that is the correct answer. So always must you choose whichever row or column you can to make your life as easy as possible. That is my humble suggestion to you. Let's look at one more example before we deal with something called Cramer's rule. And it looks like we won't be able to get through Cramer's rule today, but we can give it an old college try. Let's try out one more determinant. Again, the vertical bars mean I'm automatically taking the determinant. It's already implied by that. No, let's make it even more interesting. Let's make it more interesting. Let's take the determinant of this 3x3 matrix. Wait a minute. I can expand along any row or column I want. If I expand along that column, it's a column of zeros. I'm not even going to write that out. You should immediately be able to see that this determinant will just be big, fat, stinking zero. And that's correct. If I were to expand along this column, I'd have 0 times the determinant of the 17, 9, 2, -6 matrix. Then minus 0 times the determinant of 4, -5, 2, -6, plus 0 times the determinant 4, -5, 17, 9. But in each case, every individual thing is being multiplied by a 0. If you see this kind of problem on your homework or an exam, on the exam, you're at least going to have to just justify it in your work and say, expand along the zeroed out column, or if it was a row. And then you can just say the answer is 0 and you're done. On your homework, that's like 5 seconds. If you identify an entire column or an entire row of zeros, you're done. The answer is 0. And you can move right along with your happy self. So, enough said about that one. So Cramer's rule, and that's pronounced like Cramer, not Kramer, although I guess you can just say Kramer, especially if you're a big Seinfeld fan like myself. If you just want to say Kramer to honor the man who played Kramer, Michael Richards, then you are more than welcome to do that. But now I'm rambling. So Cramer's rule, this is going to be, it's going
Hey, real
to,
quick,
yeah.
they want to know because on the homework it's like 5.1 and 5.3. They want to know, is the rest of the chapter just not going to be on the final?
Yeah, essentially, we skip over a few sections, and I'm judiciously picking sections that are not going to be on the final.
Okay, so they couldn't be on the final.
Yeah, so y'all are good. If there was a question on the final over a section that we did not cover, go ahead and attempt it, but I'm going to compensate for that whenever I grade the finals. Because remember, I'm still going to be collecting your scratch work. In fact, your scratch work is actually required for the final. But I'm going to be collecting your scratch work, and I'm going to be considering what you do on paper, what you do. I'm going to be looking at your final. So whatever grade you get when you submit the final almost never shapes up to be your final grade on the exam, does it? You may have noticed that. So yeah, there shouldn't be any questions over material we didn't cover. If one or two happen to slip through, and you can identify that it's material we didn't cover, then just realize you're not going to be held accountable for it. So you can even skip it and come back to it only if you have time. One thing I will say, though, be very careful with that, because you could get a problem that we did cover in class, but if you didn't realize we did cover it and maybe you haven't studied as well, you might think we didn't cover it. So it's a little bit of a gambit, but I always love turning really short, easy answers into long answers. So yeah, just keep that in mind. So Cramer's rule, Cramer's rule is going to be a process that allows us to solve systems of equations by using matrix determinants. It allows us to solve a system of equations, and they have to be linear equations now, by using determinants. So that's actually really interesting. What we're going to do is let's just look at an example. Let's just look at an example. Because I think that's just going to be the gosh darn most helpful thing for you. What we need to do, we need to understand the process of turning a system of equations into a matrix. So let's say you had the simple system, a 2x2 system of 5x plus 6y equals 2. No, I'm sorry, 6. And then 7x plus 2y equals 2. Oops. Now, what you're going to do here, it's kind of a weird process, but you're going to define a couple of determinants or matrices. You're going to call it the matrix of coefficients. You're just, for the matrix of coefficients, you're just looking at this business here, the coefficients on the variables. You're not looking at this thing. This is called the answers column. And you're going to make a matrix out of that. 5, 6, written in the exact same order you see. So you need to make sure your system of equations are written with the x's first, then the y's, then if there's any z's, x's, then the y's, then the z's. So this matrix is going to be 5, 6. It's just the coefficients. 7, 2. Then what you're going to have is something called your answer column, which sounds like something from a newspaper. Josh, what's a newspaper? You wouldn't get it. But anyways, your answer column is going to be the things on the right-hand side. The right-hand side here. So it would be the column, just a single, it's like a matrix, a 2x1 matrix, if you will. So you have your matrix of coefficients, you have your answer column. Now you're going to define a few determinants. You're going to define capital D. That's what we're going to call it. This is the determinant of the matrix of coefficients. You're going to define a few more determinants. You're going to define D with a subscript of X. So we're just going to call it DX, not D generation X. We're going to define DX here. That's going to be the determinant of the matrix of coefficients, but with the answer column replacing the first column in the matrix of coefficients. So it's going to be 6, 2 will be the first column because that was the answer column. And then the second column of dx is going to be the same as the matrix of coefficients second column, which happens to also be 6, 2. That's just a coincidence that they're both 6, 2. Oops. And then dx is going to be what happens when you take that determinant. You're also going to define a dy determinant. And now what you do is you replace the answer column into the second column of the matrix of coefficients, leaving the first column the same. Which is pretty neat. Pretty neat. And then altogether, your solutions. The solutions to your matrix. So let me write that out. The x value of your solution is going to be the dx matrix divided by the d matrix. The y value will be the dy matrix divided, and by matrix, I'm sorry, I mean determinant. It'll be the dx determinant divided by the d determinant, which will both just be numbers here. And then y is going to be the dy determinant divided by the d determinant. So we just have a whole mess of computations we need to do. Let's do them. So we'll start with this one. We needed to take the determinant of the coefficient matrix. We know we need it. It's going to be 5 times 2 minus 6 times 7. 10 minus 42 will give you negative 32. So for a 2x2 system, this isn't too horribly difficult. Now let's compute the dx matrix. It'll be 6 times 2. We go along the first diagonal minus, then we go along the second diagonal. Hey, it'll just give us 0. That's okay. That's okay. Finally, the dy matrix will just be along the main diagonal, 5 times 2 minus 6 times 7 by coincidence. It's the same computation as the d matrix. And so now we're running out of space, but I can make some space here. The solutions to my system of equations. The x value is going to be the dx determinant divided by the d determinant, which is going to be dx was 0, d was negative 32, 0 over negative 32 is 0. Y is going to be dy, which is negative 32, divided by d, which is also negative 32. Y is going to be positive 1. And we just solved this system of equations. We didn't use substitution. We didn't use elimination. We used Cramer's rule. And so our solution here, 0 for x, 1 for y, so it is the ordered pair 0, 1. And that's it. We used Cramer's rule to solve this system of equations. We're done. Then just imagine if you had three variables, three unknowns. You'd have a 3x3 system with x, y, and z. You'd have the d determinant, but you'd also have your dx determinant, your dy determinant, and then your dz determinant. To find the dz determinant, you replace the third column with the answer column. We'll work an example of this next time, but you'll realize that in each case, you have to solve a 3x3 system of equations, you're going to have to solve a 3x3 determinant, same idea. And so you have a whole bunch of 3x3 determinants you have to solve. So it becomes a lot more complicated, but still doable. Y'all have a great day. It's 9 o'clock somewhere.